Welcome back to Industrial Problem Solving. My name is Dave Roysum. Here we show where to start if you are not absolutely, truly, verily certain where to begin. It is a tool I call man, machine, or material, or 3M for short. Recall from the last module the binary and tree search techniques. Here we start at the very root of all such diagnostic trees, and the place to begin, if you are not absolutely, truly, verily certain where to begin. Here, all problems have their source in man, machine, and/or materials. I say and/or because many problems, perhaps most, lie at an intersection. For example, poor machine control ergonomics lies in the intersection of man and machine, now called HMI, or human-machine interface. I devoted a dozen modules to this topic in the series labeled Web40109. However, some problems lie primarily on one of the three axes, or perhaps our personal control is mostly limited to one axis. For example, if you have baggy webs, the problem is, for all practical purposes, almost entirely in the material axis. I say almost because while a precise machine cannot make life better, a crooked machine will certainly make it worse. On the other hand, if your customer is complaining about web breaks, chances are good there are many opportunities with both your material and their machine. Your material may be increasing break rates due to nominal design, such as average tensile strength, or variation in properties, such as cracks or holes near the edges. On the other hand, your customer may have a machine that greatly exacerbates the problem with poor tension control and poor roller alignment, for examples. The problem solver must list all effective options, regardless of how politically pleasant they might be. Decision makers, such as bosses, may decide what options are pursued, but only after all options have been listed and thoroughly discussed. We'll have more to say about this in the pitfalls of problem solving section of this course. In any case, the man-machine-material Venn diagram keeps us organized, as well as nudges us to be more honest about where functional opportunities might lie. Here, we have a problem showing up on the winding roll, but with no obvious problem coming to it. Is it the winder's fault? Of course it is. But that is not a useful question or answer, because we learn nothing new from it. The real question to ask is if it had invisible help from upstream. Those of you who have been to my Web 101 class will recall that almost all complaints of bagginess on film and metals is simply a gauge profile variation that is excessive. However, even in most other materials, the majority of bagginess is related to thickness profile variations, even if there were also other causes, such as moisture streaks in paper as one example. Excessive tends to be in the 1 to 10% range. 1% web profile thickness variation is usually no problem, and 10% is usually no saleable product. Yes, nonwovens and textiles and tissue and blown film that is oscillated fast enough can take a bit more, while metal foils can usually not take even that much. Whether you can see, measure, or even control the thickness profile variation is totally besides the point. It is usually a root cause. In fact, the strongest cause. Yes, you can and should wind looser, but that is not a strong knob and also has limits of its own. Thus, while we may start with winding tightness only because it is easiest, we will usually have notable success only by leveling the web. In other words, profile variations is both necessary and sufficient to cause bagginess, while no amount of tightness can cause bagginess if the web is sufficiently level. We cover winding tightness in great depth in my Web 101 class, and we cover strategies for decision making, such as starting with tightness and then moving to leveling, later in this course. So let's look similarly at this diagram. Here we clearly see a streak coming out of the process, perhaps a coater as one example. It would be silly to involve the winder in this discussion when the material is already flawed before it reaches the winder. Again, we are going to ask a similar question. Is the process at fault? Of course it is! But that's not a useful question or answer. Again, because we learn nothing new from it. The real question to ask is if it had invisible help from upstream. I will give you an example. That is, certain coders, rod coders in particular, will always put a heavier coat weight on baggy lanes. So yes, the coder put on the coating streak, but bagginess was necessary and sufficient in this example. Another example from everyday life is painting. If you don't do good surface preparation, you can have all sorts of painting defects. Is the paint fussy? For sure. Was your surface preparation lacking? Also for sure. While we would love to have a paint that can cover anything, including wet or oily surfaces, product developers have yet to provide us with that paint, anything like that. So let's return to the theme of this module. That is, all problems are sourced in either man, machine, and or material. We will now apply this technique more carefully to the problem we just looked at, a coder streak, by discussing two new points. Point number one, if we had been more careful, we would not have jumped to a material and machine conclusion without listing the man. We should listed her first to begin with, and then dismissed it only after we observed that the operator did not put their finger on the web and make that streak. It is this kind of attention to organizational detail that will keep you from jumping to conclusions. Point number two. As we learned in the previous module, at each node of the diagnostic tree, we must have a test to see which branch you are on. Hopefully, this test is easy to do, but even if not, it must be unambiguous in its conclusion. So, how do you figure out whether the problem lies entirely with the process or also has invisible help from the incoming material? Pause the tape if you must and think about what you might try, at least for some processes. Any ideas how to figure out whether it's material and or machine? One thing you might try is to flip the raw material roll in the middle of the run. Yes, it would be more convenient to wait and flip the next roll, but convenience may need to be put on hold. The reason is, the next roll may not only be, but is different. So we will make every effort to flip this roll, rethread, and restart. If the defect stays in the same lane, then material uniformity is not in question. Yes, one might argue fitness for design in that system. Both material and machine might be fussy. But here we were focusing on one strategic question. That is, who owns the location of the streak? Is it the web, or is it the process that owns that lane? In this case, the process owns that location. The supplier still might be in trouble. They can always be in trouble, whether reasonable or not. But the customer's machine clearly has a profile flaw that is responsible. If, on the other hand, the defect location moved from the back quarter to the front quarter when the supply roll was flipped, then obviously the material owns that location. Now the supplier is in much bigger trouble than in the previous slide. Sometimes it is just not physically possible to flip the web, perhaps because it is very one-sided. Here, I don't mean that it might not meet spec. That is of little concern to the troubleshooter. What I mean is the process does not function at all on the other side. Then what? Well, in most machines we have, or should have, a small amount of sideways leeway. Yes, it may be very inconvenient and require the better part of an hour to set up in a different web location, but convenience is secondary to getting an unambiguous answer as to whether the location is owned by the web or the machine. The real limitation is whether you can find the center of a streak to a resolution less than or smaller than how much you can move the web sideways. On narrow defect lanes, this is almost always possible. On wide lanes, it is seldom possible. I refer the reader to one of the most difficult of all baggy web troubleshooting assignments I've ever worked on. See Web 201.45L on this same channel. Without clever thinking by an operator on how to determine machine or material, we would not have been able to solve a decades-old problem in that industry. The reason for the additional challenge is that baggy edges, plural, is far more difficult than a single baggy edge. In part because we can't use the flip tool. Flip a smile, and you still have a smile. So, just as with the flip tool, you might be able to determine who owns that location using the shift tool. In the baggy edges problem I just mentioned, we did not have enough room to move the web sideways. So, to make room, we pre-trimmed off one edge before we ran it. Please see Web 201.45 to show how cleverness in putting several tools together, and especially organized thinking, might be needed for some seemingly impossible problems. Let me close with one last observation. Actually, more of a critique of a common problem-solving technique. All too often, people focus on when a problem appeared and when it didn't, or how severe was it. This is a very weak technique. For defects that favor lanes, which is the great majority, location is the number one problem-solving attribute. Width is number 2, and a far distant number 3 is how bad the problem was. The reason for location being primary is that it allows you to make the very first branch on the tree, man, machine, or material. More specifically, it lets you answer the most important early question, that is, who owns the location of that lane? The flip tool, as well as its many variations, is one of my favorite of the street smart techniques. The reason is because it allows us to determine which machine to work on next. Is it the supplier's machine? Or is it your machine? Furthermore, the answers are usually so solid that most everyone should agree with the conclusions. True, the technique is not always convenient. Sometimes it's not physically possible. Sometimes it won't work well, at least without modification, for problems such as those that involve symmetry. It also doesn't work when there are too many streaks, or if the streaks move within minutes. Yet, no method or recipe is best for all situations, just as a box wrench makes a very poor hammer. Our goal is to first know as many tools as possible, and second, to select the best for any particular situation based on the laziness criteria. Thank you so very much for joining me in this continuation to the problem-solving processes. I hope I've made the case that the flip tool and its many variations is one of the most powerful ways to get started, and also helps us avoid jumping to conclusions or missing options. I hope you'll find the flip tool as one of the very best ways to be lazy early in the process. Stay tuned for a dozen more tools for the lazy.